So I didn't scare too many people away, from the first lecture. All right. There were a couple questions, mainly from ECE students about books to get. So again, the book I would highly recommend if you want to get a book is the Goodman's Fourier Optics book. He has, he'll really go through diffraction in great detail in this book, and he talks about a lot of other systems, optical systems and so forth, coherence a little bit as well. The only thing he doesn't probably cover in great detail is polarization and perhaps some, basic optical system characteristics. So again, this probably has, if you want to invest in a book, again, this is the one to get. If you need special information about things, like I would highly recommend as well maybe buying a couple of these field guides, SPIE field guides. This is from John Grievenkamp on geometrical optics. Here we go, a little better. I use this a lot too because I forget a lot of these things, and these are laid out pretty nicely. You have one page. I've been debating writing one of these as well. You have one page in order to describe something, so it's sort of like a dictionary. You look up, working distance or pupil functions or whatever you want, and you can do that. There is actually one on holography as well. Pierre Blanche wrote one on holography. He kind of jumped me on that one. But anyway, it's good too. It has a lot of, referenced one-page descriptions of things, which again can be very useful. And I believe there's one on polarization. So if you really wanted, and they're only about $25, and there's, I think, usually student discounts for them. So again, I'd highly recommend a couple of those along with Goodman's book, and you should be pretty well set. So what I'd like to start out with today is basically talk a little bit about some of the historical underpinnings of holography. I do this because it brings out, again, a little bit about how some of these ideas formulate. Denis Gabor, of course, was awarded the Nobel Prize in 1971 for his invention of holography as we currently know it. And he did this in 1948. I'll talk a little bit more about him later. But he kind of built upon things that were done prior, of course. And by the way, Denis Gabor was actually an electrical engineer who won a Nobel Prize, so that's pretty good encouragement for engineers to do good things. So what were some of the things that Gabor kind of built on? Well, probably the first idea that sort of germinated into holography was that of Abbe diffraction, and I have a little write-up here that I made on that. I kind of borrowed this picture from a Collier, Burkhardt, and Lin, which is kind of a classic book on holography, which is unfortunately is no longer in print. It was written in 1971, right at the heyday of lots of things going on in holography. And as you can see here, this violates the first principle of optics, in that light is traveling from right to left. Light always travels from left to right in optical circles. So I'm redrawing that picture correctly. But anyhow, it nonetheless, all kidding aside, it shows a kind of a double diffraction effect. And so the idea here is, so here is an object, and this object just happens to be a grating. It's a periodic structure with, or it's a structure that has holes in it at periodic spacing, okay, is the way to think of it. And then if you illuminate this with a plane wave, the subject or the object here is placed in the front focal plane of this lens. And so if you look at what happens, there is going to be a couple of different paths that the light will be enhanced at. And these enhanced directions of propagation are going to be the diffraction orders. So we essentially have, what's shown here is that there's 3 diffraction orders. So there's a 0 order, which goes, just along the axis of the system. And then there is a +1 order and a -1 order. And that occurs through each of these holes, each of these periodic holes in this structure, this object. So again, so if you place a object in the front focal plane, what happens in the back focal plane is that the light is going to be, if you place parallel light passing in this through the front focal plane, the light will come to focus in the back focal plane of this lens, okay? Just, again, a basic optical relationship. So if you look here, you see that there's actually 3 sets of parallel rays. This set of parallel rays, this set along the axis, and this set going down. So what happens is the axial set forms a focus, again, in the back focus, since these are, again, parallel rays coming through. This set up here forms an off-axis point of focus, and this lower parallel set of rays forms a point focus below the axis, all right? So that light, again, continues to propagate, and so what Abe had kind of looked at and experimented with was the fact that, okay, you can think of this now as these points here are now going to generate or serve as a new set of source points, okay? Right? Because they are, in fact, that, right? They are focused light coming down to these points. The light then from those points will expand out, and these all form spherical waves, okay? So, and these waves now, you have several sets of waves coming from each of these points, all right? And they interfere, and what they end up forming is a set of image points out here, which are magnified images of this object that we have here, all right? So again, there's this kind of wave description now for what happens when light passes through a periodic structure, a grating, or a hologram. A hologram is basically a grating. That light then forms this set of secondary point sources, and then that set of secondary point sources generate a set of spherical waves which interfere, form other enhancements in this back image plane that we have. Now this principle we'll come back to later. We'll talk a little bit about diffraction. This is really the Huygens principle, where you have the wavefront is forming, you end up with these diffraction patterns, which are superpositions of waves that propagate from the aperture. And in this case, we have a secondary set of source points that form that image, that diffraction pattern, or in this case, the image. Now, embedded in this, too, is some interesting things. We have embedded in this is, we have some Fourier analysis as well, right? We have this front focal plane. We end up with, on the back focal plane, the Fourier transform of the light, which is passing through that front focal plane. We'll go through that in a little bit more detail later when we talk about some of the some Fourier optics, kind of a review of Fourier optics specific for the class. But again, this was a rather clever, interesting thing that was developed back in the, I believe this was done in 1873, back at the end of the 19th century. So building on this, so this was Abbe. So after Abbe, Bragg, Sir Lawrence Bragg, was doing work on X-ray diffraction, all right? And so he was, this was, again, right around the turn of the 20th century. People discovered that they could generate X-rays in various ways. and they noticed, what they were able to do was to kind of form these patterns by illuminating these crystal structures with these X-ray illumination beams, okay? And so what they were actually doing, so here this is called the Lau pattern for one of these patterns, but they were really diffraction patterns that were formed by the diffraction of the X-ray fields by these very closely packed crystallographic structures, okay? So these patterns, again, you can form, by looking at different materials. So here's a nickel material and a beryllium material here. These are some X-ray diffraction patterns taken from an old book that I found. Actually, one of my students found this and gave it to me. But you can find these in many places. And this, again, is a way of analyzing atomic spacings in various types of crystals. So Bragg was playing around with this a lot. And what so his contribution to holography was to do the following. So he took a crystal, generated one of these diffraction patterns here, and then what he did was to, and these are projected over, a reasonably large area, something on the order of centimeters or so. So what he did then was to take a plate, like a thin piece of metal, and accurately drill holes where he found, he probably took a simpler structure than these, but he accurately drilled some holes in these high-intensity regions of this X-ray pattern. And then what he did was to illuminate that with coherent illumination, and what he ended up getting was a magnified image of this cell structure, okay? So that's kind of clever as well. Again, it's diffraction theory, kind of similar to this Abbe method where you're doing this. Again, Bragg he had studied Abbe's work, and so it sort of shows this ability to create these secondary diffraction patterns, which actually are the image, perhaps a magnified image of your object, okay? So again, rather interesting. And pretty close to what we see as being holography. All right. Then there were some other things that I think were quite, also significant as well. Similar to the X-ray diffraction was the electron diffraction, and so, right around the 1920s or so, there was a lot of work being done by de Broglie, showing the duality between particles and waves. And so electrons were particles, but by accelerating them to high energies on the order of several kilo EVs, thousands of electron volts, you're able to create wavelengths, again, that were on the order of hundreds of angstroms. And so that corresponds to the spacing, again, in some metallic structures like aluminum foil. And so Davidson and Germer, back in 1927, did these experiments, and they actually got a Nobel Prize for doing those experiments because it confirmed de Broglie's hypothesis about the wave and particle duality. So again, having waves that are corresponding to the spacings of atoms in materials gives rise to these various diffraction patterns. So another kind of different thing that was going on, again around 1920s and 30s, was creating acoustic waves or acoustic vibrations in material. And what this did then is to compress and rarefy that material. And when you do that, you end up creating actually a refractive index modulation. So these are standing wave patterns. You have a transducer here to generate the acoustic wave. They generate the acoustic wave, and they set up a standing wave pattern in the medium. And then if you shine a light beam through this, you end up getting diffraction from these standing wave patterns that are generated in that medium. So this is, again, as we'll see, this is basically a volume hologram or volume grating, which gives you very high diffraction, can give you very high diffraction efficiency. And this is actually, this was the first demonstration of acousto-optic modulators, okay, which are very commonly used for optical signal processing today, all right? So again, a diffraction process, setting up a volume type grating and giving rise to some interesting diffraction effects. Okay, another sort of development along the road to holography was Littmann photography. So again, Littmann was a photographer back in the late 19th century, but back then they didn't have color film yet. So he was looking for a way to form color photographs of scenes that he was trying to take pictures of. All right, and so what he ended up doing is putting a very reflective layer on the back side of a piece of film. He actually used mercury, which was, not a very good material to use, but it produced a very nice clean surface that you can be applied on the back surface of one of these photographic film plates that he had. And then what he did was he illuminated this. He created an image on the film plane here, and he ended up again creating essentially standing wave patterns for different spectral bands that were illuminating the film. And so these standard wave patterns were then recorded in the film. And again, he was kind of forming a reflection type hologram. All right, and the Littmann photography or Littmann photographs are actually very striking. I've seen a number of these. They're made without any dyes, any multicolored dyes for forming the photograph. They're all done by kind of a reflection enhancement of various spectral bands. And Littmann actually got the Nobel Prize for developing this in 1908. So again, very interesting. It still didn't have this three-dimensional quality to it. And so back in the 1940s, after World War II, Gabor was playing around with, well, not playing around, he was working on electron microscopes. And the problem with electron microscopes back in the early days is they didn't have very good lenses. So he basically didn't have a good way of focusing the light down to illuminate the object. So, and to form an image of the object with the electron beam. So what he figured was, well, what if, he was, again, an electrical engineer. So what if we do the following? What if we get rid of the lens? So we just send this electron beam, focused electron beam down, and allow it to expand. And so it illuminates the object, and it scatters some of that light, but also some of that light passes through. So you have then two waves, all right, forming. So one he considered like a carrier wave, which is providing your signal modulation, kind of stepping it away from zero frequency, and allows it to interfere with these scattered waves coming off at these various angles. Okay, and so he was going to do this for electron microscopy, but he said, well, let me first try it optically. It's easier to do kind of optical manipulation. Now the one thing he needed though was coherent light source to do this. So he was kind of forced to use a geometry like this because the sources at the time, the narrowest band sources in the 1940s were, like mercury discharge lamps and so forth, which only had, maybe a few millimeters of coherence length associated with them. So he couldn't allow the path separation to be very large. So he he had to come up with this configuration, which is called, a Gabor hologram or an inline hologram. And later we'll see, although this works, you look at this, these are some of the images here. So this was the object, this is the hologram, okay, the interference, and this is the reconstruction. So, it looks a little better than the hologram, but it was pretty striking at the time, and it really, it kind of stimulated some thought and some interest, but because of the fact that sources were not very coherent then, things didn't really go very far. Okay, so it wasn't until Emmett Leith back in the 1960s, another electrical engineer, he was working on radar systems at the time, and Leith and Upatniks, they developed an off-axis geometry. They also used a mercury arc lamp, but the way they did it in a rather clever manner by filtering the diffraction orders, passing the light through a grating, taking one of the diffraction orders, and then using that light to illuminate the sample. Okay, so they were able to further filter the light, and they actually came up with the first off-axis hologram, which eliminated some of the problems that are associated with this configuration. We'll talk more about those later and see how that see what the issues are, and then see how they're corrected by some of these other geometries. Okay, so that's kind of the history of holography. Now what I'd like to do is talk about, kind of give a baseline of information, of terms, and kind of fundamental ideas that we'll be talking about throughout the class. So this is kind of still a introduction, but we'll get a little more specific here, a little more detailed. So first thing, let's look at a holographic construction. Or the holographic construction process. So what's involved in making a hologram? Well, first thing, again, it's an interference recording, all right? And so we have a reference wave and an object wave. And so the idea is, if we just record the object wave, we're going to lose the phase. But if we interfere it, we can record, we're still going to record the intensity, but embedded in that is going to be the phase. And so we'll see how that embedding takes place. So when we set up these two beams here, our reference and object, we're going to form a set of fringes. And these fringes always form, first rule of thumb here, if this is the angle between these two beams, these fringes are going to bisect that angle, all right? So it's half the distance between those two. So we form these fringes, optical fringes here, and we can model that or explain that by an intensity, again, which is, as I mentioned last time, coherent summation between or of this object and reference wave. And so this gives rise to r squared plus o squared plus r o star plus r star o. All right. So that is the field that we have here. So we have this is sort of the bias, and this is actually where the fringes come to play in that fringe plane. All right. So the next thing that we're going to do, so we have these two fields coming in, and we have to make the hologram some way, right? So we have to make a physical thing. So we place a recording material here. So this could be, say, our film. And this then, what this does is converts this intensity pattern that we had into a transmittance function, okay? So we go from intensity pattern to a transmittance function. So we have T now is going to be proportional to that intensity pattern. All right, so this proportionality constant comes about by the processing of our film, or whatever the change in that material whatever that change is that happens in that material by exposure to light. And so we simply have this function here times this constant. So again, we have this set of bias terms. And we also have the modulation term. So we have alpha times O R star plus R star O. All right, so this would actually be the hologram, if you will. And it's a physical thing, okay? It's something that we physically can see, like, you know, the holograms I brought in last time. Okay, so this is kind of the first step. The second step, the next step is the reconstruction. Okay, so in the reconstruction process, we now take this hologram that we've made with our grading structure. It's actually a transmittance function, which could have modulation in all directions. And we let's illuminate it with the original reference beam, R. Okay, so here's the original reference beam. And so what we end up getting, let's look at. So we have the reconstruction beam, I sub R here, is going to be R times this T of x, y, z, right? That's what we're doing. And so what we have is this is now equal to R times alpha times these bias terms. So those aren't too interesting for us for now. And then we have plus alpha, and we have R. And notice here, so we have R star O plus alpha times R O star. Okay, so this term is just kind of a zero order term. It's just some intensity that passes through. We then get this, and also we have this term, which, you know, is really not too much, I should say. I mean, it's just a term here which comes off at some other angle coming out of the material, but it doesn't really look like much. It has the phase of R twice, and then the phase of O star. But so that's this term. That's this term. But the interesting term is this last one in this case. Because notice we have R times its complex conjugate, right? So again, if we have e to the j phi R times e to its conjugate, e to the minus j phi R, we end up with 1, and we're left with e to the j phi O, which is that object field, right? So what we end up generating is the original object field coming off that hologram. So again, that's really the basic idea of holography, is that by combining with this reference field, we can cancel the phase, these kind of varied phases that we get for the object field, and we end up generating the pure object field for that wave. Okay, we may have some junk fields coming out here, but again, we can definitely get that original object field phase reconstructed from this system. Okay, so we can generate the object field, but by illuminating with the original object or reference field. But we can also do something else, which is very useful. All right, so let's do a reconstruction, not with R, but with the conjugate of R, R star. Okay, so what is the conjugate? Well, the conjugate is kind of a reverse phase field. All right, so if we're coming in here with the reference field, say in this direction, it's kind of a time reversal of that field. So we would illuminate it with a wave that counterpropagates that. So that would be, if that were R, this is R star. It's kind of the counterpropagating field direction. So this is the conjugate or the phase conjugate reconstruction for that hologram. And now let's look at our relationship that we have. So we have I, and let's call this R sub R star. So now we have R star times T of x, y, z. And again, T is equal to the sort of the constant that comes about through development times the intensity that was used in the recording. So we have R star times alpha times, again, R squared plus O squared, sort of the bias field, the average field, plus alpha times R star, O star, and then plus alpha times R star, O. Okay, so again, we're going to end up with a kind of a zero order field here, which is that one. We have also, now this one was the one that gave us the useful object phase reconstruction before, but now we're illuminating with R star, so we have R star times R star. So we have, e to the minus 2 j phi r for this phase, and then we also have e to the, say, j phi r here. So we don't really get that, I'm sorry, phi 0, the object phase. So we don't really get the accurate object phase reconstructed. But this term now, here we have e to the j phi r, e to the minus j phi r, e to the minus j phi o, which is the phase conjugate phase for that term. So here, these cancel, and we're left with the phase conjugate, okay, so of the object field. So we end up with O star, all right? So there's lots of useful applications for this, and one of which you'll actually do some work on during the lab demonstration experiments is making a holographic lens, okay? All right, so if we have let's look at that for a second. We'll do this a number of times. We'll use it throughout the class here. So how would we make a holographic lens? All right, well, what's a lens generally is a Fourier transform device, right? It takes you can think of it taking a plane wave and generating a delta function, right? So if we put a delta function or a point source here, and we allow that to be our object field, like this, and we then come in with we could come in with a wave along the axis, but that'll cause a little bit of overlap problem. So let's come in at an angle with a plane wave. Still a Fourier transform lens. It's just now we're going to get a little better result when we reconstruct this. All right, so here we have O and R. All right, so we make our hologram, do the recording, and then we're going to reconstruct this. All right, so and by the way, all right, so here again is O and R, and this is also O and R down here. So notice what happens in this holographic lens is, again, the fringes are going to form along the bisector between these two waves, like that and like that. So the fringes are going to kind of rotate. The orientation of those fringes are going to rotate in that holographic recording. And later we'll see that the spacing of those fringes are going to vary very significantly. I'll go over that a little bit later. But for now, we can just use this little rule that we found earlier to find what the orientation of the fringes are. And we see here directly that, they are going to definitely change orientation as we go across that lens. All right, so we make our hologram. We have a transmittance function. We now re-illuminate. So let's first re-illuminate with the original reference field, all right? Just extend that out. So now we come in here with this. And so what are we going to get? Well, the original object field that we have is going to kind of look like that. If we extended it out, it's going to keep expanding, right? It's a point source. By the way, we could actually make that an aspheric by sort of pre-aberrating this too. So we'll talk about that later when we talk about various holographic lenses we can make. But for now, we'll keep it as a spherical lens. So if we were to illuminate this with the plane wave, what we'll generate is that expanding spherical wave coming out. All right? So it's going to look something like that. If you were to look at this out here, what you would see is kind of a virtual point down there, or on the other side of that hologram. Okay, so that's fine, but it's if we want to use this as a lens, right? We'd actually like to focus the light down to a point. So if we now take this holographic lens and illuminate it not with the actual reference here, but with the conjugate, what we'll end up getting then is light which comes, again, it's coming back to, it's still the object wave, but the object wave on this side is light that focuses down to a point. All right? And so you can actually make a holographic lens which takes light and focuses it to this point, or if you had, light at some specific distance away from the lens, the holographic lens, it will image that light or it will image that object field to a image. All right. So again, there's some interesting things that you can now do, even using just this very simple hologram construction and reconstruction process that I mentioned. So and occasionally on a midterm or something, I'll say, what's the holographic process? Well, the holographic process is that 3 or 4 step process that I just went through. Forming the interference pattern, recording it in a medium, and then reconstructing it. Okay, and along with the equations that describe the production of the different phase terms that we may want, either the original object or the phase conjugate. Okay. All right, so a number of constructs are quite useful. So again, we're talking about terminology here. So useful constructs that we could utilize. So we were talking about R. R is a complex field, and O. And again, we can look at this from a couple of different perspectives, and we will in class. But generally, this is going to be some amplitude function and a phase function, e to the j. And we can think of this as being kind of a, basically as a plane wave with some phase, all right? So we may have omega, so when we're talking about this plane wave propagation, omega t minus k, the propagation vector, dot r. So the propagation vector is, the vector corresponding to that field. So we can associate with this k, or this r star, a k vector. K vector, it is a vector, and it's going to be 2 pi n over lambda, and sine theta in the x direction plus cosine theta in the z direction, where, say that, usually those are referenced relative to the z-axis. By the way, in this class, I'll typically use z and x, and y is coming out of the plane for coordinates. But again, this is a vector which, again, corresponds as well to the Poynting vector for your field. And it's a very useful parameter that we'll be using throughout the class. All right, so we have, this would just be our plane wave, but we can also have some additional phase associated with that. So we may describe it in that manner. And also we'd have our a sub o for the amplitude e to the j omega t minus, right, a little kr there, k sub o dot r plus phi sub o. All right, so if we were then to, we can kind of put this in the form of, another useful form. Again, if we look at, we can do that by doing the following. So we have I, again, is equal to r plus o. Again, these are complex terms squared. And so, again, so what we'll have is r squared plus o squared plus r o star plus o r star. And so what you can see now is that, this time part's going to drop out of all this, and we'll just need to worry about the phases. But let's write this out, and you'll see, again, a relationship to some other things that you probably run across. And if not, you'll see it for the first time and see that it's, again, very useful. So we have the amplitude of the reference field squared, the amplitude of the object field squared, plus AR, AO, e to the j. And then we have kr minus ko, that dotted with r, plus phi r minus phi o for the reference and object field phases. And then plus ar, ao, e to the minus j with the same argument, k sub r minus k sub o, dotted with r, plus phi sub r minus phi sub o. And this is, we can also see that this is just equal to the following: ar squared plus ao squared plus 2ar ao cosine of kr minus ko, again dotted with r, plus phi r minus phi o. Okay, so here, this is sort of the classic interference relationship, where we have a kind of a cosine modulation of the fields, and superimposed upon that is the any additional phase modulation difference that we might have from the reference and object phase, right? And this is an intensity, okay? So what that means is, if we put a piece of film there, we can actually record that. And so you end up with this modulation, again, which represents this phase difference between these two field phase values in that intensity pattern. Okay, so again, it's just a little demonstration of how this phase can be extracted from an intensity pattern, if it wasn't completely clear before. And again, we'll use, plane wave analysis a lot because it's much easier. The first thing to do when you're analyzing a complex field problem is look at plane wave solution, because regardless of whatever that field is, if you take a small enough little area here, that is a plane wave. If we keep cutting that aperture down, you end up getting a plane wave. And so it's quite useful to look at that at various different points and then maybe sum up the whole set of values. I'm actually doing this in a problem right now. I've been perplexed trying to solve this one problem. And I keep reading these papers where they have all these, these horrendous integrals. And it's just much easier to just do a little kind of partial ray and partial physical optic analysis of this thing and get a good intuitive feel for it. So it's a very useful thing, even for old guys like me, to use this. So anyway, we're going to use plane waves a lot because they're very handy and useful for lots of different things. Okay, so let's look at hologram, some other things relating to classification of holograms. So again, we've talked about this a little bit, but basically a hologram it's a set of scatterers, all right? So we have a medium which is periodic here with some period capital lambda. And these are something that's going to produce optical scattering, okay? So if we illuminate it again, we're going to get some kind of scattering field, and that scattering field is going to be enhanced in certain directions coming off this, okay? Now, so what are these scatterers? All right, well, it could be a modulation of the conductivity of the material, and that conductivity is going to give rise. Generally, we don't talk about conductivity too much in optics, but we talk more about absorption. So we could have an absorption modulation of this grating. So if that's the x direction, so we would have some absorption modulation, or we can modulate the permittivity. Again, we don't usually like to talk about permittivity a lot in optics, but we do like to talk about the refractive index. All right, and so this kind of sinusoidal recording, right? This is the intensity pattern, which we're then going to form a transmittance function of by. I'm going to use a different symbol here since I'm using alpha there, which is basically proportional to that intensity profile. So we have this cosinusoidal modulation of the refractive index or the absorption in that medium. Okay. Now, if we were to illuminate this medium, generally, to make a good hologram, what you'd like to do is to utilize the permittivity or the refractive index, because that produces a phase modulation. Whereas absorption, that produces an absorption or an intensity modulation. Right? And if you modulate the intensity or you modulate the absorption, you're eliminating some light, you're absorbing some light, right? So the phase modulation is going to give a higher diffraction efficiency. Grading, right? So if this is, again, if this is our incident intensity and we have some diffracted field coming out there, the diffraction efficiency, again, is just equal to that diffracted light over the incident light. So what we'll see later in making, doing some analysis of the diffraction efficiency is that, the best you can do with a absorption modulation as far as efficiency is somewhere around, 6%. About 6.25 for a very thin absorption grading. Whereas for a phase grading, you can get 100% efficiency if you, get rid of your Fresnel reflection losses at the surfaces and make the grading characteristics correctly. Okay, so generally, again, this phase modulation is the way you want to go in setting up your grading. Now, fortunately, there's a lot of materials that are very good phase modulation materials and very, very useful for that purposes. Okay, what else do we have going on here, all right, as far as kind of classifications of grading structures? Well, one classification we can make is whether is the relative thickness of this grading to other optical parameters, okay? So we can kind of break this down into a thin hologram versus a thick hologram. So what do we mean when we say that we have a thin hologram, other than drawing it really skinny, okay? What do we mean, what thin relative to what? Okay, that's the question you should ask yourself. Someone tells you it's thin, okay? Well, of course, we have the thickness, d, but, also with, when we're talking about optics, right, one of the things that we're concerned about is, what's the light wavelength, right? So we also have lambda, all right? So in a thin hologram, the wavelength is actually, we can say, is much greater than the thickness. So what we're really saying here is that we have like point scatterers. I don't know if scatterers is a true word. It probably would be underlined in red in Microsoft Word. But anyway, point scatterers is what you have here. Because, again, relative to the wavelength, it's small. And, there's not too many things that much smaller than wavelengths in optics except points, all right? The other thing, though, is what other parameter do we have? Well, we also have the grading period, right? So when we talk about thin, we're talking about relationship to the period. And the wavelength here is going to be actually much smaller than the period, okay? So it's like it'll only scatter once in going through the thin grading. So again, so we only have a single scatter process in passing through the hologram. Or in passing through the grading, all right? And again, that's going to limit the efficiency of that grading because we don't get much enhancement in going through that, all right? So the next thing that we can do then is look at, let's sort of cascade these, okay? Let's make this much thicker, all right? So we now have a thick or volume hologram. And again, these terms refer to these parameters, okay, that we have in order to define what's going on. So in a thick or volume hologram, we now have, we can draw it thicker, okay, so here's our D now. Here's the period. These fringes could be, slanted in some way. They don't have to be oriented perpendicular to the axis. So here maybe is our axis again, like so. And so now we have that the period is now going to be much less than D for this thick or volume hologram. The period is going to be comparable to the wavelength, all right? So again, so we have that requirement. And so what this means is that the wavelength then is also going to be much less than the thickness, all right? So what does that imply? Well, that implies that the light interacts many times in passing through this medium. Okay, in passing through. So one way to think about that is that we have, so the light's coming through here, all right, illuminating this sample. And so we can kind of break this down into a series of thin slabs, like so. And in each of these, there's going to be scattering occurring. Like so. All right, so the light scatters, but then there's other, it's still in the medium, okay? So it's going to have to rescatter from these planes. So one of the features of this thicker volume hologram is that when these requirements are satisfied and we have these multiple interactions, there is a very selective character to the grading and to the directions in which the fields that can diffract and make it out of that hologram, there's a very limited set of directions that are allowed. Okay, it's almost like a band gap. Okay, so I mentioned this last time. A hologram is kind of like a photonic band gap, where if you have a band gap, if you don't have, here's your valence and conduction band. If you don't have enough energy, you can't propagate. Okay, so here, what happens is you get this dephasing effect, as the light propagates through here, and so there's only a set of select paths that will go through. All right, one is the zero order, okay, and one is the diffraction order. All right, for this grading, it's kind of like a Venetian blind kind of effect. If you have louvers and you kind of look in a certain direction, that direction will go through. Yeah.
So, what's the effect if you change the thickness on the light that exits, the amount of scatter that goes on through the hologram? Because if we look at the single one where we have one scatter for a very small d, it's in the order of much less than a wavelength. If you change d slightly, then it looks like you change that drastically as well too. So
yeah. Well, again, you have the orientation of these fringes, and so the preferred direction for going through this is the direction in which diffraction, which we'll define here with the grading equation, and reflection from these fringe planes, when these are equal. Okay, so even though you change that thickness, right? What that will do for you, if you reduce the thickness but keep everything else, these fringes in the same orientation, what's going to happen is the efficiency is going to change. So what will happen when the efficiency changes? Well, you'll have less light being pulled out of this illuminating field. So again, there's this coupling of the fields, right? So you're either going to go in the zero order, or if you do this right, you'll just get one diffraction order. And the light will, in transmission mode, it'll interplay between those two. Okay? And so there's some other things you could play with too, like the index modulation. All right? And so I showed this curve last time, or this figure last time, where this idea of the volume grading creates selectivity in the diffraction efficiency profile. So there's another thing which we haven't gotten too far into yet, but again, it kind of depends on the index modulation. So we can still make a pretty efficient volume grading if we decrease the thickness, if we increase the scattering by increasing the index modulation, we can still get high efficiency, but now the selectivity kind of is diminished or expanded. Okay. Similarly here, if we make it very thick, what we'll see is we actually have to diminish the amount of scattering, because otherwise we'll kind of overmodulate the grading, and it'll rise, the efficiency will increase and decrease, start to increase and decrease, provided there's no residual absorption in the material. So there's this real interesting interplay between the different parameters, and you have to control those properly in order to get the effect that you want.
And are those the big three properties: the thickness, the diffraction order you're choosing for your fringes, and then your index?
Yeah. So
change. Are those the big ones that you're going to?
So the efficiency is going to depend on, just as a little, it's going to be a sine squared function of pi delta n d over lambda cos theta. Later we'll derive this, but this is the kind of the grading strength parameter that we have. So we have this index modulation, and we have the thickness, which are the two main components in determining what the efficiency is. And notice here, this particular function, this is for a transmission grating here, which I'll define shortly, is a sine squared function, which means that it could go up and down and up and down and so forth. This is, again, for a pure phase grating. Okay. So, yeah, your questions are very good, and, we'll see how we can control these. And by the way, so this index modulation, the way we control that is by controlling the response of the material. And the way you do that is by the exposure time during your holographic recording process. Okay. So I mentioned, a transmission and reflection grating. So I guess I should define those. So transmission hologram is, we've talked about it quite a bit, but basically the fringes are oriented more or less perpendicular to the surface of the holographic recording material. And when we illuminate this, if you think about this volume grating here, we'll get a diffraction order which passes through or is transmitted through the medium, hence the name transmission hologram. Okay. So we have a transmission grating, and then if we orient the fringes parallel to the surface, like so, and we then illuminate this, then we get this kind of phase scattering being enhanced from all these different surfaces, and we end up with a reflection diffraction order. Okay, so here's the reflection hologram geometry. And by the way, this particular hologram is very similar to an interference stack. So if you're making, for instance, anyway, name escapes me here, but we have a high-low stack of refractive index, and so these give you a index modulation, right? High-low, we're talking about index, so we have again a index modulation that looks like that. You can either make that by deposition in McLeod, right? Yeah, McLeod does the thin film course, right? So you can do that by deposition, but you can also do this interferometrically. And the modeling for these in holography is done exactly the same way as using a chain matrix rule for the high-low stack modulation. Okay. All right. So, kind of moving along again. So, when we actually make a hologram, all right. So I kind of pointed this out last time, but for the most part, we'll use lasers except for some special purpose situations, and then we'll have a beam expander and spatial filter here, and so we'll focus that light down through like a pinhole here to clean up the beam, the laser beam, allow it to expand, and then collimate it. And basically then form an interferometer. This is a beam splitter which allows 50% to pass through here and 50% here, and then we do the recording down here. This would be your film plane for the recording. If we did it this way, we would get just plane wave recording like so, but and then whether one is called a reference and object is sort of can be reversed. But if you wanted to record, say, a hologram of a chess man or some object like that, what you would do then is just place, maybe tilt this off at a little bit different angle, place your object out here, and light that's scattered from that would then interfere with the reference beam in order to do your recording. You can also pre-aberrate or do something to your reference beam here, so you can do some other kind of field modulation here. Or, as we'll discuss this later with the imagery, but sometimes a pre-aberration is necessary to get good reconstruction fidelity in the hologram. All right. So there's some useful figures for looking at and considering what type of hologram you're actually going to get. So in my notes, I think my posted notes, I have this figure. So here we have a reference source and an object source point. And so these are kind of iso fringe lines, okay? So they're just showing the fringes that you would get by interfering light that comes from these two point sources. So you see here that we end up with a transmission hologram with those fringes oriented more or less perpendicular to the surface. We can form a reflection hologram here with light coming from both sides of the surface. So the fringes are, again, oriented more or less parallel to that surface. And here is the hologram corresponding to the one that Gabor made. Remember, he had that reference source point out here. There was an object scatterer. It wasn't really a source, but it was just something that scattered light. So the light would come through here, and it would scatter and then interfere with the residual light that comes through. Now, the problem with the Gabor hologram is that when we re-illuminate that, we have an issue. All right. So here again is the source, the reference source. Here's the object point, and then you do the recording like this. And so the light hits this, and then it scatters as well, like that. All right, so we record the hologram, and now we want to reconstruct it. So when you reconstruct it, you put your source point out here again, and it scatters. It will, well, there's no point out here, I'm sorry. It will create a virtual point out here. You'll be observing it, say, out over here like that. So you'll see the image of that source point, but it's a virtual image. But you're also going to get a, remember that R star to R star term, okay, or the RR term times the O star. So this would be your RR O star. It ends up, that's forming something that looks like a real image, the conjugate. There's the light actually focusing here. And you also have, the reference field. So when you're trying to view this, you see all of these kind of overlapping. So it's kind of a problem when you're trying to do that. Okay, so it's not the best geometry, although it's good enough to get the Nobel Prize. So, so it wasn't that bad, right? Okay, so later we'll see how we can eliminate that by changing the geometry, and we'll look at it from a couple of different ways. All right. In the remaining couple of minutes, I'd like to start deriving a simple relation that is very useful, and we'll be using it throughout the class. And that is the grading equation. All right, and so for this, the grading equation refers to surface scattering, or we could think of this as our thin hologram that we just went through and kind of defined in terms of other parameters. So again, so we have we have a set of surface or point scatterers, and those will be, say, in the x direction. Here's the z direction. These are separated by a period, cap lambda, and we then illuminate it with a plane wave like such. All right, and so now what we want to do is we want to look at sort of various directions that come off here after the light scatters. So we have this distance, which is equal to the period. We then have, of course, if we look at the wavefronts that we have, one wavefront corresponding to this diffracted or this scattered field goes in this direction. So this is the wavefront corresponding to that. The wavefront for this one is like so. And so we end up having some different path lengths for these two waves. So here, again, that's perpendicular to those propagation vectors. And we have, let's label this A, D, C, and B. All right. And here we have a angle of incidence, theta sub I, and a diffraction angle, theta sub D. All right. So let's just write a very simple relationship here. So if we look at this, we have this path length and that path length. So if we write AB minus CD, that's the path length difference. And whenever that path length difference is equal to an integral number of wavelengths in that medium, so this might be in a medium n. So whenever that's equal to an integral number of wavelengths in that medium, lambda over n, we're going to see enhanced scattering. Because we have basically like a interference effect or a superposition of the waves. They're in phase, okay? All right? And if we then write A, B, and CD out, right, then we can say that we have lambda sine of our diffraction angle minus cap lambda, which is the period, sine of theta sub I equals m lambda over n. Or finally, we can just say sine theta d minus sine theta I is equal to m lambda over n divided by the grading period. So this equation, simple as it is very useful in holography and diffraction. And this is called the grading equation. All right. Now, this grading equation, it describes, as I mentioned, the surface scattering condition. It's also the condition for surface, the field matching at the interface of the diffractive element. Okay, so this is going to be very useful in determining the direction of the diffracted fields that we get off the hologram or the grating. Okay. All right. So I guess that's probably a good place to stop for today. Anyway, so you now have a number of useful tools. This grading equation, again, is going to be extremely useful. You're going to use this till you're sick of it in the class. But again, it's something that helps you predict really very easily where the diffracted light's going to go. So remember I mentioned last time we have the image quality and the efficiency characteristics. So again, this is only telling us a little part of the story that we need yet. But again, it's a very useful part. So, okay, have a good weekend, and I'll see you on Tuesday of next week. So.